Morning, everyone. We're going to get started in just a minute or two. Just a reminder, um, Lab 12, the TAs will have their lab sessions today. So please try to get started in the lab, and the TAs are there to help. I also just sent out an email. The email that had this live stream link in it also had a poll that if you could please fill out today or tomorrow, just about some options for the final class. So I'm considering um, having a class talking about the coronavirus epidemic and the ways that a lot of the techniques we've used in this class are being used right now by people trying to do things like plan treatments or make decisions about what kind of policy responses to have. And so I recognize that people may not want to be hearing about this in class. Other people may think that it's interesting. So please just let me know. Either way is fine with me. The traditional final class is just sort of a general survey of stuff that we didn't get to talk about. um, but yeah, if you're interested in doing this different kind of final class, just let me know in the poll. I just put out the schedule for the rest of the class on this slide, just to show we're getting close to the end here. So next week we're gonna have two classes about Bayesian statistics, and then we'll have that final week. There's going to be kind of a summary class. The analytic strategy class is going to be kind of a summary class, and then we'll see what we do for that final lecture. There's today's lab, which is lab number 12, and then there's homework 11 is due next week, and homework 12 the week after that. So yeah, if you have any logistics questions, feel free to let me know. Okay. All right. So today we're going to be talking about another kind of general concept in statistics, which is called power analysis. So we talked on Tuesday about effect size, right, which was a measure of how big of a difference we saw between groups, or how big of a relationship we saw between different variables. And so effect size is not the same thing as statistical significance, right? You could have a big effect that you're very uncertain about. You could have a small effect you're very sure about. But in general, it's true that bigger effect sizes means that it's easier to detect this effect. Right. So in some sense, it's sort of obvious, right, that if there's a really big difference between groups, it's going to be easier to detect. But what we do with these power analyses is try to be a little more precise, right? To think about, based on some quantitative measure of this effect size, we can make some quantitative statements about exactly how hard it's going to be to detect this effect if it's real. So we brought up this concept of power a few times in the past. For example, we've discussed the power efficiency of tests that make different kinds of assumptions. And right, just to remind you, power is the probability that we will correctly reject the null hypothesis when the null is false. Right, so what power is that if the null is false, meaning that there really is an effect, what is a chance we're going to be able to detect it in this sample? And we can never guarantee we're going to detect true effects, right? There's always a chance we're going to just get a terrible sample, right, with really unusual participants in it. But we can say something probabilistic, right? That if we have a powerful study, it means we're going to detect true effects more often, right? A powerful study means that if there is a real effect, we will be able to find it in most of our samples. So yeah, there's a question here about what if the null is true, and so power has nothing. Power doesn't say anything about whether the null is true. So there's sort of two competing things here. We want, if the null is not true, we want to be able to detect that it's not true, and that's what this power is. If the null is true, we want to make sure we don't reject it, and so that control over that false positive rate when the null really is true, that's our traditional alpha threshold, right? So if we have a 0.05 alpha threshold for our p-values, right, to reject the null, then that means there's a 5% chance that if the null is true, we're going to incorrectly reject it, right? So there are these two different things that are that they they're related to each other in the sense that there's sometimes a trade-off between them, right? But they're two different concepts. If the null is true, we want to not very often reject it, right? We want to have low false positives. And we also want high power, which is that if the null is false, we want to correctly reject it, right? So those are two different parameters in our analyses. So when we're trying to determine this power threshold, it's going to depend critically on the effect size. So if the effect is really small, then it means that we're going to really need to be very confident about it in order to reject the null hypothesis, right? That if there's only a small effect, it means that we need to, we're going to have to, for example, collect a large number of participants or make our measurements more precise. And so, yeah, there's a question in chat too about the symbols here. So yeah, alpha is our control on false positives. So an alpha of 0.05 means that we should only get false positives 5% of the time, right? What that means is that if the null is true, we will only reject it 5% of the time. So that alpha controls our false positive rate. And then we also have this power, which is basically 1 minus the false negative rate, right? So if the null is true, we don't want a false negative. Meaning we don't want to fail to reject the null when the null is false. And so so there's this power, which is the same as 1 minus beta, I think we've mentioned before. And so what we want to have a low chance of false positives and high power to detect true positives. Right. And so those things also are going to be somewhat in conflict, right? As we'll see in the lecture here, if we want a really low alpha threshold, if we want a really low chance of false positives, that's going to hurt our power, right? It's going to make us also less sensitive to true effects. And so this kind of analysis where we look at how all these factors relate to each other is called power analysis. So power analysis in almost all cases has to be done before we actually perform an experiment. And we'll talk near the end here about why we can't do this afterward. But the idea is that before we perform an experiment, when we're planning our experiment, we want to figure out how big of an effect size we're looking for and how big of an experiment are we going to need to run. And so the first thing we need to do is speculate about what the effect size is. This step is pretty hard in practice. If we really knew what the effect size was, then we wouldn't need to do our experiment, because that would mean we already knew there was a true effect and we knew how big it was. But we could at least get a rough idea, right? That if this effect is real, how big would we expect it to be? Sorry if you missed any further there for a second. So if this could also be related to practical concerns that, for example, with some kind of medical treatment, if it's not going to improve outcomes by more than 2% or something, then maybe we're not interested anyway, right? So we have to have some idea about what effect sizes we expect to see and what effect sizes we care about. So then what we're going to do is using this speculative effect size, we're going to predict whether we'd be able to actually find this effect size depending on our sample size, right? And so the idea is that if we run an experiment with this sample size and there is a true effect of this size, how often will we be able to find it? And again, we can never guarantee we're going to find real effects, even big ones, but if we plan out how big our experiment's going to be and what size of an effect we're hoping to be sensitive to, then we could say, what's the chance we're actually going to detect that effect? These analyses can sometimes yield quite surprising results, in the sense that this power, or 1 minus the false negative rate, can sometimes be a lot lower than you might think. The sizes of studies that we run in psychology are often driven by very practical concerns. So for neuroimaging studies, for example, it costs something like a few $1,000s per subject. And so we might be constrained primarily by money. But if you actually work out these power analyses, you could see that for many of these studies, we're probably underpowered, meaning that our sensitivity to true effects is lower than we would like it to be. And then we'll talk later on in this lecture too about even in cases where we do reject the null, meaning we have evidence in our sample that the null is false, if our sample size is small, then it can actually be quite hard to interpret what we should believe after running this kind of study. Okay, so let's work through an example of this. So one of the simplest cases we can think of is a one sample t-test. And so this is where we have a single population and we're comparing the mean of this sample population to some null hypothesis. All right, so we have this x bar, that's the mean we're measuring in our sample. We're comparing it to some null hypothesis, which is usually 0, but could be something else. And our t-statistic here is we divide by, this is the standard error of the mean, right? This is how much variability we would expect to see if the null is true. And so we talked last time that you could also, if you this standard error of the mean, right, has this square root of n term in it, which tells us that as our sample gets bigger, there's going to be less variability in the mean. And if we kind of factor that out, right, this piece here without this factor of n in it is Cohen's d, right? This is the effect size measure that is not dependent on the sample size, right? That's just the denominator here is just the our estimate of the standard deviation in the population. And so if we expect an effect size of d, then we'd expect to see a t-statistic of something like d times the square root of n. Right, what this tells us is that there's a relationship between t, which is our measure of confidence that we actually see an effect, right? It's related to our effect size, but it's not the same because it gets scaled by the size of our sample, right? So to get if we want a big t-score, meaning we want to be really confident and reject the mean because we're so confident, we need either the effect size to be big or we need n to be big, right? If the effect size is small, we're going to need a much larger n. So there's a question in chat about what counts as a small sample, and it really depends. For neuroimaging, like for fMRI analyses, even a few years ago, it was relatively common to have experiments where you had maybe 10 or 12 people that you scanned, which is quite a small sample size. Nowadays, fMRI sample sizes are more like 30 people. For behavioral experiments, it's a little bit easier to get more subjects, especially if you can run them online. So now we're starting to have much bigger sample sizes. A lot of this also depends on the population you're targeting. So, for example, running experiments in infants is much more difficult to recruit infants. Unfortunately, the effect sizes in infants also, these Ds also tend to be pretty small because this S is pretty massive, right? So when you're trying to get an infant to do a study, the chance that they're actually paying attention to anything you're saying is kind of low. And so this variability in the outcomes is really huge. And so so developmental work is one where this is really challenging, where D is pretty small, and getting this big N is also quite challenging. So developmental labs usually have people on their staff, and their only job is to try to recruit as many people as possible. People have also tried to come up with other solutions for this, and there's been lots of initiatives recently of trying to have much bigger sample sizes. This is through online studies, as I mentioned, also things like pooling resources across labs. There's a few of these many baby studies that basically involve a number of labs all recruiting from local infant populations. And so, and again, this equation here is just what we're expecting. This equal sign is not going to be true in practice, right? This will depend on the individual sample that we get. And so we could get kind of unlucky and get a t-value that's lower here than what we're expecting. So what power analysis is going to tell us is if we want to have a good chance of getting a t that's above our critical t threshold for rejecting the null, how many subjects are we going to need for there to be a good chance of that? Okay, so let's think about an example here. So again, this is a one sample t-test. And let's imagine here that the true effect size is a d of 0.2. And so again, this is a relatively small but not unreasonable effect size. And And let's imagine that we have 50 subjects. Okay, so so the way this is going to work is we construct our null hypothesis. So the null here is that there really isn't an effect, right? And so we have our t distribution. It's centered at 0. This is a t distribution with 49 degrees of freedom, right? So it's pretty much a normal distribution at that point. And this t distribution defines a critical t threshold, right? So if we are doing a two-tailed t-test, we're going to have thresholds at both plus and minus 2 here. Right, and what this tells us is that in our sample, if we observe a t-statistic that has an absolute value that's bigger than 2, then we're going to reject the null, right? That 95% of the time, the null, if there's no effect, right, if there's really a null effect, we're going to have a t-score that lands somewhere between -2 and 2. If in our real sample we see something bigger than 2 in either direction, then we're going to reject the null. Okay, and then so if the true underlying effect here is a d of 0.2, then the sort of true distribution of t-scores we're going to get looks like this. We'll sometimes call this the alternative hypothesis, right? All the alternative means is that it's not the null, right? So in this case, this is the true underlying distribution of our t-scores. And the center of this distribution is centered at this expected value, which is that we have a d of 0.2 and n of 50. So we would expect on average to get a t-score of about 1.41 from when we're taking samples from this population, right? So the red here is the actual sampling distribution of the t-score. And these little dotted lines here are from our null hypothesis. There's a question about whether this has to be two-tailed. This is just, for this particular example, we're doing a two-tailed test here, right? But this power analysis idea is a very general one. So it also works for one-tailed tests. It also works for things that are not t-tests at all. So you can do this for ANOVAs and correlations and pretty much anything. You'll see in the lab today, you'll be doing, I think, mainly t-tests, but that same package, you'll see, can also do correlations, and it can do lots of other stuff that's not in today's lab. Okay, so we don't actually see this red thing, right? This is like what's actually generating the data. We don't get to see that. We make our null distribution here. We have our thresholds, and then we're going to run our experiment, and we're going to get some t-statistic in our sample. And so this red distribution here is showing what kind of t-statistics we're going to tend to get in our sample. And so you might see that there's a problem here, which is that we're only going to reject the null hypothesis if we get past this critical t-value of 2. So the power of our experiment is this area here, which is the area under our true t distribution that's greater than our critical t-value that we got from our null hypothesis, right? And so if we, so this red curve here is showing where we're going to tend to get t-values in our sample. Again, we don't actually see this curve. This is like the world that's generating our data. All we're going to get to see is a single sample from this red distribution, right? We're going to run our sample. We're going to get a single t-score out of our sample. And if that t-score lands somewhere bigger than 2, then we will correctly reject the null, right? Because the true distribution here is not the null distribution. The problem is that this yellow area here is not that big, right? So this is only about 29% of the area under this red curve is greater than 2, right? And so what this means is that even though there is a real effect in this data, about 70% of the time, the t-value that we get in this data is going to be somewhere over here, right? It's going to be somewhere that's less than 2, that's less than our critical threshold. And so because of that, we're going to fail to reject the null, right? So this experiment has relatively low power, meaning that a lot of the time, even though there really is an effect here, we're not going to be able to see it. So what could we do to improve our power? So one thing we could try to do is improve our effect size. There's some parts of the effect size that maybe we don't have any control over, like right, what impact this intervention really has on people. But there is part of the effect size we have control over, which is the denominator, right? So We do have control to some extent over this variability here, right? If we could make more precise measurements, for example, then we could decrease this variability. But maybe the simpler thing to do is just change n, right? So what we could do is instead of 50 people, let's try with 150 people, right? And so the effect size here is still 0.2, but we just added more subjects. We tripled our amount of subjects. So now we should expect t values that are a factor of a square root of 3 bigger, because we've tripled the size of our population, of our sample. And so you can see that moved this red curve over, right? This red curve here is centered around this t value, which depends on the square root of the number of people in our sample. And so now our power looks much better, right? This yellow part of the curve that's above our critical threshold is much bigger. So here we now have a power of 68%, right? Meaning that that in this case where the null is false, we're going to realize that it's false 68% of the time, right? It's going to be only about 70% of the time are we going to be in this bad zone here where we got a t-score that's kind of ambiguous, right? We got a t-score that we're not sure if it's from the null or not. Right. Most of the time, we're going to see a t-score that unambiguously couldn't have come from the null because it's bigger than this critical threshold. All right. Let's take a brief quiz break. And yeah, happy to see all the questions. Feel free to ask any other ones. So the power of a study is the probability of what? Rejecting the null when it's false, rejecting the null when it's true, failing to reject the null when it's false, or failing to reject the null when it's true. All right, so which one of these is power? All right, I'm seeing mostly A's, which is right, which is that when the null is false and we correctly reject it, that's the power of our study, right? So we want to have that if the null is, when the null is false, we want to reject it, right? That's a good outcome if we reject the null when it's false. Right, the terminology here is always a little bit weird because we're talking about the null, right? When the null is false, that means that the effect is true, right? There really is a true effect. But again, for this null hypothesis framework, really, we only talk about either rejecting the null or failing to reject the null. So yeah, we haven't talked at all yet about how you actually get these numbers, how you'd actually compute them. In the lab, you're actually just going to use a library that helps you, right? But the intuition here is that we're computing the area under this red curve, which is bigger than this critical threshold. Right. So so in this example, there really is a real effect, right? It has this effect size of 0.2. And so when there really is a real effect, then our t-scores are going to come from this red distribution. This is the distribution that's actually generating our t-scores is a t-distribution with 49 degrees of freedom that's centered at 2.45, right? And so whenever we run a study, we're going to get a t value that's sampled from this red distribution. Sometimes we'll get t values that are close to 0. Sometimes we'll get ones that are way out here at 4 or even bigger, right? And when we get that, we compute that t value in our sample. We're going to compare it to this critical dotted line here, right? This critical t-score, which is coming from the null distribution, right? So this null distribution is centered at 0. It's a t-distribution centered at 0 with 49 degrees of freedom. And so we could just look up in a table or whatever, right, that the critical t-score here is, the degrees of freedom here is 149, right? Because we've increased our sample size. So, right, both of these are t-distributions with 149 degrees of freedom. This one's centered on 2.45. This one's centered on 0, right? And so we can't actually see this red thing, right? But we can construct this blue thing. The blue is just our assumption. Our null assumption is that this is effect centered on 0. It's going to have the shape of a t-distribution with 149 degrees of freedom. But so based on that, we can figure out our critical t value, which is around 2. And again, this critical value also depends on alpha, which is an important point here, right? That this power calculation is going to depend on this alpha threshold that we pick. So we can work out this critical threshold here of 2. Then we run our experiment, which means we're going to get a single sample from this red curve. And if this sample comes out over here greater than our critical t value, that's good in the sense that we can correctly reject the null. If it comes out over here, it's bad, meaning that even though there really was an effect, we're going to fail to reject the null. Right, so the area of this red curve that's above our critical value is our power, right? It's a chance of correctly rejecting these effects. And there's also a question about what this formula looks like for other tests. I don't think we're going to show any other explicit formulas. This can get kind of complicated for other tests. So usually what people do is use one of these libraries in R, like the one you're going to see in the lab today, which does these computations for you. You can imagine a kind of brute force way to do this is just by simulation, which is often what we do for complicated models, right? So we, for a complicated model, we just assume what if the world works this way, right? What if there's this effect size and we sample it in this way? Then we could get a distribution of what we'd expect to see, right? I don't know if there's any like other easy ones, but you definitely could do this kind of analysis for things like regressions. You could also do this kind of thing for non-parametric rank tests, right? And so you can, in general, either by simulation or formulas, you can come up with what this distribution is going to look like. This red distribution of true outcomes is going to look like if there really is an effect of this size. And then that'll tell you your power, right? So the ingredients we need to compute our power is we need to figure out what our threshold is going to be, which is going to be like a T or an F or something threshold, right? And that'll depend on the alpha we pick. And we also need to write down what our hypothesis about what the true effect looks like, right? And that's this red curve. And so if that really is the true effect, then how likely will we be able to find it in the sample? Okay, so there's another way to think about power, which is about what the p-values look like. And so, let me switch these around a little bit. Okay. So we talked last time about or maybe this was last week, we talked about if the null hypothesis is true, then the p-values that we're going to expect to get out of the study should be uniformly distributed between 0 and 1. Right? This is sort of what the definition of a p-value is that if the null hypothesis is true, then a p-value of 0.05 means that we're only going to get this outcome 5% of the time, right? We're only going to get an outcome at least this big under the null about 5% of the time, right? And so the p-value distribution under the null hypothesis is going to be uniform. So now the question is, what does our p-value distribution look like as we start having a real effect, right? And so if we have just a tiny little effect, here's a tiny little effect of, maybe a little bit bigger. Let's do 0.2 maybe. So if we have a relatively small effect here, this blue curve is showing what our p-value distribution is going to look like, right? And what this is a distribution over studies, right? So the idea is when we conduct a study, our p-value is going to be sampled from this blue curve. And so you can see, first of all, there's a lot of area of this curve that's out here. And this is all our like false negative regime, right? Here we got a p-value that was above 0.01, above 0.05, even though there really was a real effect, right? So this is a kind of bad zone out here where we failed to reject the null, even though it is actually false. And over here is the good zone, right? Where we correctly got a low p-value. Right, when we get a p-value less than 0.05, we don't know if it's a false positive or not, right? But our chance of landing here in these small p-values is higher if there's a real effect compared to if there's not, right? If there's no real effect, we're only going to get a false positive 5% of the time. If there is a real effect, right, then now our chance of getting a positive here is our power, right? If there really is a real effect, our power is the area over here, right? The chance of getting a p-value that's less than 0.05. And so you can see as our effect size gets bigger and bigger, right? So if we have effect size of 1 maybe here, right, which is pretty big by psychology standards, you can see most of the p-values here are really tightly clustered around 0, right? We can sometimes get unlucky. There's still some p-values that are out here, right, that are above 0.05, but most of the time, if we have an effect size of d equals 1 and we have n equals 30 people in 2 groups, this is assuming an independent samples t-test, then 97% of the time we're going to get a p-value that's over here less than 0.05. Right, so you can see that there's sort of 2 inputs to this. There's the effect size, there's also the sample size here. So if we make our sample size smaller, let's say only 10 people, then you can see now our power has dropped down to 60%. The chance of getting a significant p-value here is only 60%, right? And so for example, I mentioned that people used to do neuroimaging studies with like 10 people per group. And you can see this is a little bit worrying. Like if you have like truly enormous effects, let's say like a d equals 2, then there you really only need a few people, right? So even with like 5 people per group, almost right 90% of the time we can still detect it, right? And so yeah, but for things like that are more typical in psychology, let's say 0.3, something like that, you can see in order to get a reasonable power here, we really need to make the groups quite large, right? So even with, here's 100 people, even at 100 people, this d of 0.3 is pretty hard to detect, right? We're only like a slight majority of the time are we correctly rejecting the null here. So this way of thinking about it with these p-curves is like, right, it's equivalent to the way we were thinking about it here in terms of some separation between the distributions, right? It's the same, it's just a different way of plotting the same thing. But yeah, this sort of shows us, right, our goal here is to get this, what we want is that the null distribution and the alternative distribution, meaning our hypothesis about what the effect size might be, we want those distributions to be kind of far apart from each other so that when we sample from whatever the real distribution is in the world, we want it to not look like the null, right? Assuming that the null is not true, right? We want that if there's something really going on, samples from that really going on world don't look like samples from the null world. Okay. So when we say a study is underpowered, what that means is that its sample size is small relative to the effect that we're trying to look for. Right. What this means is that, well, so there's a few different problems with underpowered studies. So one is that, first of all, most of the time they're not going to work, right? So even if there's a real effect, if your power is low, that tells you that most of the time you're going to get a statistic in your sample that looks like a null statistic, right? And so what this means is that getting a null here, for example, is not going to be super informative, right? So getting a value that you fail to reject the null, it's not going to really help you because that's going to happen most of the time, even if there is a real effect. There's another problem here, which is that if they do reject the null, they're going to typically exaggerate the true size of the effect. And we're going to walk through an example of this in a few slides of how this happens, right? But the intuition here is that, let's look at this example here. The only time we reject the null in this example, where we were kind of underpowered with 50 people, is when we're in this yellow region over here. And all the t values in this yellow region over here are bigger than the average expected t value, right? And so what this tells us is that if we reject the null here, anytime we're rejecting the null, we're going to overestimate what we think the effect size is, right? The only way to reject the null here is to get kind of lucky in our sample and get an effect in our sample that's bigger than average. And so if we get this above average effect in our sample, we'll reject the null, but we're probably going to be misinformed about what the correct effect size is. And finally, there's also a chance that we could get a significant result in the wrong direction. So remember, for a two-tailed test, right, we have a critical value on either side. And if our true effect size is pretty small, and so our true distribution and our null distribution are pretty close, then many of our significant effects are actually going to be on the wrong side. And we'll again work through an example of this too. Right, and so this is one of the reasons why we do these power analyses ahead of time, right, is trying to like work backwards from a significant result to the effect size is usually not going to be a legitimate thing to do. But this is really useful for figuring out how big we want our samples to be. Remember, we also talked in the multiple comparisons lecture that it's not legit to start with a small sample and then collect more and more subjects until you get a significant result, right? That's a good way to get lots of false positives if you do things that way. What we really want to do is determine our sample size before we start and then run that many people, right? And so this is really important. We need to know we need to figure out how to set that number before we started collecting any data. And so this is probably the main use of these power analyses, is determining this sample size, right? Is planning out, if we want to measure this effect, how many people are we going to need? It's useful, first of all, for making this decision. Okay, we need 100 people. We're going to collect 100 people and not stop until we've collected 100, right? It's not going to be good to stop somewhere in between. It could also convince us that maybe we just can't do this study, right? That we might do this sample size calculation and realize we're going to need like 1,000 people, and there's just no way to collect that many people from this population we're interested in. So calculating these sample sizes by hand you're basically always going to have to use some kind of table or R or something, because they depend on these areas under T and F curves and things like that, right? And so because of that, because they involve these areas, these integrals under these curves, you're going to need to have some kind of either pre-integrated table or R or something to help you do this. So there's a table in the textbook for computing this thing they call delta. Delta is basically just T. They're using delta to mean that this is a speculated value of T. So it's not something we're actually measuring. It's just like our guess of what effect size we think we'd like to detect, right? It could be based on prior work. Again, it could be based on some kind of practical consideration about what effect size we think we care about. So the idea is when we're planning our study, we're going to compute this delta, which is the speculated value of the speculated value of T for the true effect, if there is one. And so there's going to be slightly different formulas for computing this, depending on the test that we're doing, right? So again, this is all in t-test land, but even in t-test land, right, there's several different versions of t-tests, and they have slightly different ways of computing T, and so they'll have slightly different ways of computing delta. And so we can also use this in reverse, meaning that the way we're usually going to do this is this way, where we look up a desired level of power. So instead of fixing delta and then computing the area under the curve, we're going to say we want a certain area under the curve. So we want like 85% power. And then we can figure out what kind of delta we're going to need in order to get to that level of power. So for example, if we have like a delta of 3, then we could try to work out what this tells us about D and N, right? So if D is something that's fixed, then we can calculate what N we're going to need. And so again, you can do this for basically any test. We're just going to work out the example for the t-test, but the logic is basically the same for any of these tests. So here's what the delta table from the textbook looks like. So each row here is a different value of delta. And each column here is like a different alpha level for our significance test. And so a kind of default power people often use is 85%. Again, it's going to depend a lot on the situation, that how much you care about this trade-off between alpha and power. Right, there might be situations where having a really low power would be really bad, or maybe situations where having a really low alpha might be bad. And so, so this kind of depends. But something around 85% usually is like a reasonable trade-off, where 85% means most of our experiments are going to work, but we don't need to have an enormous sample size. And so most of the time, we're probably going to be in this column here, right, which is our two-tailed 0.05 column. So if we set our alpha to 0.05 for a two-tailed test, then we're in this column here, which means that we're going to need a delta of 3 in order to achieve 85% power. Right? What this means is that we want to plan our tests so that we're expecting to get a t-score of about 3 in our samples. Right? That if this effect has the effect size we think it may have, then we want to plan things out so we can get a t-score of about 3 in our samples. And if we do that, then if this effect really exists, which with the size that we think it does, then we'll be able to detect it 85% of the time. Okay, so yes, let's say we're doing a two-tailed alpha 0.05, we want 85% power. And let's say we want to be sensitive to effects that are d of 0.02 or bigger, right? So if there's a true effect that's at least a Cohen's d of 0.2, we want to be able to find it with this experiment with 85% probability. So for in the one sample t-test, right, we showed that the formula for t here is d squared of n, right? And so so if this speculated value of t here has the same formula. For the two sample t-test, it's basically the same, except that the n here is actually the n within each group. And so at least if these are two equally sized groups, then we have the square root of n over 2 here as the scaling factor. So if we just rearrange these formulas and solve for n, we can get these other versions of them that will spit out a sample size, right? And so the idea here is this formula tells us that if we're aiming for a t-score of 3, for example, and we have an estimate of our d, we can just plug into this formula to say, well, how big is n going to have to be to achieve this level of power? So for example, if we plug in these numbers here, right, we get that for a one sample t-test, we're going to need about 225 people in order to detect an effect of 0.2 with 85% power. For a two sample t-test, again, it has this kind of worse scaling where it scales with the number of people in each group. And so it's going to end up being twice as big, right? So for a two sample t-test, it's telling us we're going to need 450 people total in order to detect this effect. Right, so you can see in general, right, the formulas here, right, we have this scaling where as d goes up, we're scaling with 1 over d squared for our n, and then we're also scaling with delta squared on the top here. And again, delta is something you're not going to be able to compute. You're going to need to look it up because it basically depends on areas under t distributions, right? And so you're not going to be able to figure that out by hand, but yeah, so, and again, also you can see the thresholds here. If we're willing to relax our alpha threshold, if we're willing to have 10% false positives, that drops our delta value, right? And that means that also is going to drop our n, right? Because remember, n is proportional to delta squared. So if we're willing to have more false positives, that means that we can drop our delta and we can use a smaller sample size, right? Conversely, if we want to be really stringent here, right, we really only want 1% false positives, that's going to boost our delta up to 3.6. And what that tells us is that if you really are going to be this strict on rejecting the null, you're going to need more people to correctly detect real effects, right? This means we're being really conservative with rejecting the null. We're going to need bigger samples to be confident enough to really reject the null. We're going to be less sensitive to true effects. Okay, here's a quiz about the sample size calculations, right? So for these kinds of t-tests we've talked about, if our effect size doubles, then to achieve the same level of power, we're going to need the same number of subjects, half as many, twice as many, or a quarter as many. Okay, so if we're trying to study an effect that's twice as big, and we want the same level of power, how many subjects are we going to need? So I mean, one thing we can think about is whether the number of subjects should go up or down, right? That if our right, so if our effect size is bigger, is it going to be easier or harder to detect things? Right, so I'm seeing B's and D's, which are both in the right direction, right? If the effect size is bigger, then we're going to need fewer subjects. And the question of whether it's B or D, right? You might have to peek back at these formulas here, right? Our sample size here is scaling with 1 over D squared, right? And so that tells us that the right answer here is D, right? That we are only going to need, if the effect size is twice as big, we're going to have a 1 over 2 squared factor here, right? And so if our effect size is twice as big, we're only going to need a quarter as many subjects, right? And conversely, this means that if our effect size gets cut in half, we're going to need 4 times as many subjects in order to detect it, right? So the scaling means that we're pretty sensitive to effect size, right? That these small effects are getting like quadratically harder to detect. Right. So yeah. So for this one, the answer is D. That if we could increase our effect size by a factor of 2, and maybe we could, have like twice as accurate measurement or something. If we can increase our effect size by a factor of 2, we'll only need a quarter as many subjects in order to achieve the same level of sensitivity to true effects. Okay. So there's another type of t-test we've talked about, which is a paired t-test, right? Where we have multiple measurements from each person. So we have 2 measurements from each person, and then we compute a difference between those measurements and then just stick them into a 1 sample t-test. And so there's often cases where we have a choice when running our experiment of whether to do a paired t-test or to do an independent samples t-test, right? We could get 2. So what we could do is, for example, if we have we're trying to measure the impact of some drug on patients, we can measure some measure of health of these patients before and after we give the drug. We could measure that in the same people. So we could measure for each person, we get a before and after measurement and subtract them. Or we could measure one group of people before the drug and then a different group of people after the drug, right? And then that would be an independent samples t-test that doesn't have any pairing. And so in general, there's an advantage to having these paired t-tests, which is that it gets rid of just baseline differences between people, right? That since we're doing the subtraction, it means that if certain people are just overall healthier or less healthy than each other, that's not going to impact our analysis at all. Whereas in the independent samples version, that's going to add extra variability to our measurements, which is going to hurt our effect size. And so the amount of benefit that we get from this pairing depends on the correlation between the 2 measurements we're getting for each person, right? And so this is a population parameter that we don't know, but if people's pre and post scores are highly correlated, meaning that a lot of what's going on with their health has nothing to do with our intervention, right? It's something that was there at pre-test and is still there at post-test. So let's assume maybe there's like a row of 0.7 is pretty high, right? That means that there's a lot of similarity in these 2 measurements we're getting for each person, right? And what that means is that there's a lot of stuff that's specific to this person that's going on that has nothing to do with our intervention. And so that changes our equation here, that now instead of the n over 2 we got for the independent samples t-test, instead there's this extra factor of 1 minus rho down here. And so because of that, that means that our sample size also ends up getting reduced by this 1 minus rho. So in this example where we're assuming the correlation is 0.7, what that means is we only need 0.3 as many people, right? We end up multiplying our 450 by 0.3 down to 135. Right. So what this tells us is that if we're in a situation where we expect these like pre and post scores, right, or whatever these paired measurements are, if we expect them to be really correlated with each other, meaning that there's a lot of across subject differences that have nothing to do with the experiment we're running, then it could be much better we could be much more sensitive to true effects if we run this as a paired test, right? Meaning that we run this as a within subjects experiment where we get both of these measurements from the same people instead of from 2 separate groups. Right. And so instead of just sort of hand waving that this is a good thing, right, we can calculate now how much this is going to help. Right. So like in this example, right, if there really is a correlation of 0.7 for each of these scores, then that means that this makes our experiment much easier to run. Right. Running this as a within subjects experiment, we'll only need 135 people to get to the same level of sensitivity that we would need 450 people for in the independent samples version. Right, and so this is so we if we have the right, so yeah, so I'll repeat that whole section. So if we have the choice when running an experiment to run a within subjects experiment where we get 2 measurements from each person and then subtract them, or an across subjects experiment where we get 1 measurement from one group of people and then a different measurement from a different group of people, the paired t-test is almost always going to be at least as good. Right, this within subjects version is almost always going to be at least as good. And it might be way better if there's a high correlation between these 2 measurements that we're getting. Right, so for almost anything kind of health related, this will usually be true that there'll be a high correlation, that people's health at the beginning of our intervention at the end are usually going to be very highly correlated, right? It's unlikely we're going to completely change someone's life in just this short intervention we're doing. And so if there are those high correlations, then a within subjects experiment is way more sensitive because we can subtract out those baseline differences. In the independent samples version, those baseline differences are just part of the variance in our measurement, which is a bad thing, right? That means that it's hard for us to separate what's happening because of our experiment and these baseline differences between people. And so, right, what this means is that we would need, if we want to have the same level of sensitivity in a between subjects experiment, we're usually going to need more people. Right, and you could also, right, so it might also be that we need so many people, it could be hard to do. Maybe even if we could do it, even if we could get 450 people, maybe what we should instead do is we could run 3 experiments if they're within subjects experiments, right? Maybe we should spend our time and money in a better way. Of course, there's a couple of caveats here. I mean, first of all, this kind of analysis depends on us guessing what the correlation is going to be. And so we may not know. I mean, again, this is going to be some kind of speculation. If we really knew the exact correlation, we wouldn't have to run the study. Right. So that means that this power analysis is really more of an art in the sense that it's going to require a lot of speculation, and it's really best done by people that have domain expertise, right? That if you know a lot about the phenomenon that you're studying, then you could make relatively good estimates of these things. The other caveat is that there's a lot of things we just can't run we can't run within subjects versions of, right? So there's lots of characteristics about people that we can't randomly assign them to. For a lot of like perception memory studies, if we wanted to try teaching material in 2 different ways, we can't do it in the same person, because once we've taught them with one way, then they've already seen the material and we can't teach them with the other way, right? So there might be reasons we can't do this, but if we can do within subjects experiments and we think that there are lots of baseline differences between subjects that are going to cause high correlation in our 2 measurements, then we could have much more power in that within subjects version. Okay. So now I'm going to walk through an example of what can happen with small effect sizes and underpowered experiments. So one thing I mentioned before is that one thing we don't want to do is run some experiment and then afterward run a power analysis to say, was our experiment big enough or not? This is called a post hoc power analysis. People definitely still do this, but it's really pretty hard to interpret this. And one problem is that if we, as we'll see in this example here, if we do get a significant result, then it's likely we're overestimating our effect size in these small samples. And so our post hoc power analysis will tell us that our experiment was well powered, when in fact it wasn't. Okay, so we're going to walk through an example of all the issues that come up with these underpowered studies. So let's assume that the true effect size in the population is 0.1. And so this theta here is just like the true population value of Cohen's d, right? So there's a tiny effect and our sample is pretty small, right? So we have n equals 30 people and we're hoping we're going to be able to study this pretty subtle thing. So before we even run the experiment, right, we could think about things like, what's the chance we're going to get a significant result, right? So if there really is a true effect here of 0.1, of theta equals 0.1, what's the chance we're going to be able to find it and correctly reject the null? If we do get a significant result, how big of an effect would we need to find in the sample? And also, what's the chance we're going to get a significant result in the wrong direction? Meaning we're going to see an effect that's, we're going to reject the null, but for the wrong reason, right? For a sample that's in the wrong direction. So this is what this situation looks like in terms of our distribution. So this blue thing is the null hypothesis, which is just a t distribution centered at 0 with 29 degrees of freedom because we have 30 subjects here. And so, yeah, and then here is the true distribution, right? This is the distribution we're actually going to be pulling t-values from. Any particular sample that we collect, when we compute a t-value in that sample, we're going to get something from this curve, right? So the blue thing is, again, the null hypothesis we're constructing. The red thing is the actual way the universe works, and that's where we're going to pull a single value from this red curve. So based on this null distribution, we can set up our critical thresholds, which again are around 2 here. So so we build our null hypothesis, this blue thing, we set up our thresholds, and we say, okay, let's measure a t in our real sample. If this t is bigger than 2 or less than -2, then we're going to say that we're going to reject the null. We're going to say this is a real effect. So so the first question here is, what's the chance of getting a significant effect? And so you can see this looks like a bad situation because there's a lot of this curve. So again, the red curve is like the actual distribution that our t's are coming from, and a lot of it is between -2 and 2, right? So 92% of this red curve, which is the true curve that's giving us our t-scores, is going to give us a t-score that's not going to reject the null, right? It's going to give us a t-score that's too small for us to reject the null. So our power is just this little green stuff out here, right? Which is that 8% of the time, this red curve is going to give us a t-score that's that has a magnitude bigger than 2, right? So even though there is a real effect here, we're only going to be able to actually see it 8% of the time. 92% of the time, this experiment is going to fail to reject the null. Right, so this is warning number 1, is that if you go looking for a small effect using a small sample, you're probably not going to get a significant result, right? Even though you didn't do anything wrong, right? It's just that this experiment is too small to actually except in 8% of the time, we're not going to be able to actually detect this true effect. Okay, so that's problem number 1. Problem number 2 is, let's say if we do get a statistically significant result, right? We actually are out in this right tail here. So we got kind of lucky and we correctly rejected the null. How big is the effect size in our sample going to have to be for that to have happened, right? And so this critical t threshold here of 2.045 corresponds to a d of 0.373, right? Remember, this is our formula here that t scores are the same as d scores scaled by the square root of n. And so what that tells us is that if we do get a t-score that's out here greater than 2, when we go to compute the Cohen's d in our sample, we're going to get a value that's at least 0.373, right? It'll be even bigger than that if our t-score is out here somewhere bigger than 2, right? And so what that tells us is that if we do get a significant result in this small sample, we're going to way overestimate the true effect in the population, right? So when the effects are very small like this, it's impossible for us to ever get an unbiased effect, right? What's going to happen is that the only way to get a significant result here is for us to get a kind of weird sample where the effect size is bigger than it's supposed to be, right? The only samples for which we're rejecting the null are these ones that are out here in the tails, which don't really look like the typical sample, right? A typical sample is this red vertical line here. That's what most of the time we're going to get, right? That's like if we got something right on this red line, that would give us a reasonable estimate of the population effect size, which is 0.1. But instead, we're going to get these way overestimates. And so, but basically what this sort of means is that the only way we can get significant results is if our sample is an outlier, right? If our sample is one of these really weird ones, that's where we're getting like we're doing way better than we should on average, those are the only ones that are going to be significant. And so that means that we're going to way overestimate the effect size. Right. So this is especially bad if we combine it with kind of like some of the p-hacking techniques we talked about last week. So if, for example, let's say we run a whole bunch of these tiny studies. So we have these like n equals 30 studies are like kind of easy to do. So we run a whole bunch of them. And we're getting, right, most of these are failing. Most 92% of them are failing. But after we run like 10 or so, we finally get one that lands out here. Right. And so it's finally significant. We're happy. We file drawer all of the data that didn't work, and we just publish this one that worked. Right. And so if we do that, then these significant ones that work are going to be only these weird ones where the effect looks way bigger than it actually is. Right. And so, and again, there's techniques people try to use in the literature to detect this kind of thing, where you can basically see that that small studies, for example, might tend to overestimate effect sizes compared to bigger studies. And then there's the last problem, which is maybe like the most severe kind of problem, is that we might also get a significant result, but in the wrong direction. Right. So there's some green out here, meaning there's some area under the red curve that's above 2 in the right direction. But there's also some area under the curve that's in the wrong direction here. It's not that much area, right? It's like less than 5%. But the problem is that of all the green stuff here, so of all the significant results, this green area over here is actually not that much smaller than the one that's on the right. Right? If we compare the size of these two things, of the significant results, about 10% of them are in the wrong direction here. Right? So we only get a significant result 8% of the time. But of that 8%, about 10% of that 8% is over on this side, right? And so what that means is that if we're only reporting these significant results from these tiny studies, probably a lot of them are actually in the wrong direction, right? We rejected the wrong tail of the null, right? And so this is sort of especially bad, right? We're saying that we rejected the null for the wrong direction, meaning we're saying that there is an effect here that's actually in the wrong direction of the real effect. Right. So just to summarize the problems that come up here if we're running an underpowered study, right? The first is that if we are running a study that's underpowered like this, we're going to get tons of false negatives, right? We're going to, if our power is low, that means that 1 minus our power is the false negatives is going to be very high. The second problem is that if we do find a significant result in an underpowered study, it probably means that we're way overestimating the effect size, right? It means we got a weird sample where the effect just happened to be really big. And then maybe the most distressing thing is that if we find a significant effect in these underpowered studies, there's a somewhat decent chance it's in the wrong direction, right? So not only is the magnitude wrong, it's not even, we're wrong about what the actual interaction is between the groups and the outcomes. Okay, so we're going to do a two-part quiz here. I'm going to ask 2 questions about these underpowered studies. The first one is, let's say we run an underpowered study and we get a negative result. That means there probably is no real effect. There probably is a real effect we failed to find. We should run the same underpowered study again, or D, almost nothing, right? And here, we're assuming here this is like a real study. We don't know if there's an effect or not. We run a tiny sample of people for an effect that we think, if it exists, is going to be small. What should we conclude if we get a negative result from this kind of study where we're trying to study something small with a small group of people? All right. So yeah. So if we run we're trying to study some kind of subtle effect that we think might exist, but if it exists, it's going to be tiny, and we do this with a small number of people, and we run the study. We don't get a significant result. What should we conclude from that? That it's a true negative. That it's a false negative. We should just run it again. What should we conclude? Yeah, I'm seeing some D's, which is the right answer, right? Which is that getting a negative result in a study that's poorly powered basically tells us nothing, right? That if there is no real effect, then 95% of the time we're going to get a null result. If there is a real effect, we're still going to get a negative result most of the time too, maybe like 90% of the time or something, right? And so what this means is, right, if we run a small study trying to find something subtle, we're probably going to get a p-value that's above 0.05, and it basically doesn't tell us anything, right? It could be that it's coming from the null. It could be that it's coming from a true effect that was just we just didn't detect. Right, we basically can't conclude anything. Okay, so now part 2. What if we run this underpowered study, right, where we're trying to study something subtle, and we use just a small number of people, and we get a p-value less than 0.05. We get a positive result. What should we conclude? It's probably a false positive. The result we got can't be a good measure of the effect size. We are sure about the sign of the effect at least, but maybe not the size. Or D, we should run the same study again. All right, so yeah, what should we take away from a positive result? All right, yeah, I'm seeing a few B's, which is right, which is that getting a positive result, it doesn't mean it's a false positive, right? As long as our alpha threshold was set properly to 0.05, then we should be getting, right, that if the null is true, we shouldn't be getting that many positive results. So it doesn't necessarily, it could be a false positive, but not necessarily. But B is definitely true, which is that the only way we could have gotten a significant result in this small sample is if we got lucky with our sample and the intervention worked like really well in these people for some sampling, right? Some maybe by chance or something, right? That the only way we could have gotten a significant result is if our intervention worked better than average, right? And so whatever effect size we're measuring in the sample is almost certainly an overestimate of the true one. We have a decent idea about the sign of the effect, which is C, but we're not actually 100% sure. It could be that we got something in the wrong direction. And running the experiment again might not be that useful. If we run it again, we're probably going to get a negative result, right? And that's not going to tell us that much. So there's been a lot of discussion of some of these issues in psychology over the past few years. This, again, is related to the replication crisis, which I discussed in the p-hacking lecture. A lot of this kicked off with Daryl Bem's papers showing that the methods people were using to assess significance probably were not that robust. So there's this paper in 2015 where basically what they tried to do was replicate a number of recent psychology studies. And so what this plot is showing here, each dot is a study that was attempted to be replicated. On the x-axis is the effect size in the original publication. And so you can see all of these x values here are positive, right? They're like maybe around 0.3, 0.5 or so on average. And then on the y-axis here is the effect size in a replication. And so you can see some of these worked well. So these blue ones here are ones where the effect size in the replication was pretty similar to the original study. But a lot of them are not. So a lot of these red ones here, right, showed an effect in the original sample, but have close to zero effect size in the replication, right? Most of them are at least in the right direction, right? They're like above this dotted line, but if they're non-zero, then they're much smaller than they were estimated to be in the original studies. The size of the circles here have to do with basically the power of the replication, meaning how big of a sample size did we have in the replication. Right. So this shows us a few things. One thing is that it shows us that estimating a estimating this effect size from a single experiment, especially if that experiment is pretty small, is probably not that good of an estimate of the true population effect size, right? And so, right, and another thing that it tells us is that a lot of these studies really don't replicate that well. And so people have had a lot of different reactions to this among like different bigwigs in the field. I mean, one response is these people doing the replications are like either doing them in bad faith, meaning they're trying to tear down stuff, or maybe they're just like, or they're just really bad experimenters or something, right? The replication people are like causing a big fuss over nothing. Maybe the replications are like well intentioned, but they aren't. But the problem isn't really bad as it looks. That like the replications maybe are not replicating the way that they should. They're not setting up the experiments the way that they should. Maybe saying like, there are some people in other subfields of psychology or neuroscience that do bad stuff, but not my field, right? We do everything right. Or just like terror that like everything is broken. And so, there's like a lot of opinions about this. Definitely, if someone tells you that this isn't happening at all, that's definitely wrong. There's definitely issues. I think the field has made, even in the past 5 years, the field has made a lot of changes in the way that experiments get designed and reported. And so I think we're certainly trending in a much better direction. I'm also maybe a little bit in this camp of there are certain areas of psychology that are, for example, not very theory driven. And so it can be harder to estimate which experiments we think are plausible versus not. But certainly, as I mentioned, even within neuroimaging, definitely the effect size, the sample sizes we were using a few years ago were really totally inappropriate for the stuff we were trying to study. We now try to do a better job of power analyses and things like that. There's also been a big effort for things like data sharing. So for several of the studies in my lab, we're using databases of hundreds of people that have been contributed by multiple researchers, right? And so I think this was mostly a good wake-up call for the field, that we really need to change the way that we are planning these studies and doing statistics on them. So there's also, it is in general often the case that replication studies tend to have smaller effect sizes, right? And for a lot of the reasons we talked about in the p-hacking lecture, right, that it's really easier than 5% to get false positives, even with an alpha 0.05. This almost certainly means that effect sizes are inflated in published studies. Some of the advice in the textbook about this, I think, is not right. For example, they say that a significant effect is more impressive when it's based on a small sample, which I wouldn't really say is true. I mean, that most small samples that are run fail to reject the null. And so the ones that you see published are a biased sample of these small experiments, right? And so these small studies with small samples have much more uncertainty about them, right? They're much more likely to either be false positives or to misunderstand the effect size. So we've been running larger studies, right? Trying to increase power, right? At the very least above 50%. We can also use replication to sanity check dramatic claims, right? Check things in another sample. And we can also try to improve our effect sizes, right? The other way to improve our power is not changing our sample size, but to change the effect size. So things like minimizing variability across subjects, right? Trying to keep our groups homogeneous, trying to make our measurements carefully, things like that, right? Using repeated or paired measures whenever we can. All right, I'll do one last quiz before we wrap up for today. Right, which of these makes a finding in psychology more likely to be true? Conducting it in a large sample, getting a small p-value, or seeing it replicated in an independent sample, or all of the above? This is maybe one of the easier questions. Okay, you can go ahead and respond, right? Which of these would be helpful? The answer here is D, right? Which is that all of these are useful kind of signals we can use, right? That something is a real effect, that we saw it in a big sample, that we have high confidence, right? A small p-value means we have high confidence this didn't come from the null. If someone else replicates it, right? These are all good things. Okay, so to wrap up, right, effect size is related to power, meaning that if we speculate about what kind of effect size we're hoping to find, we can then do a power analysis. And specifically, we can do a sample size determination, saying how big of a sample are we going to need in order to study something of this size. Underpowered studies, which is what many of the studies in the field were, especially up until recently, right, can be quite misleading. The only way they can show a significant effect is by having an inflated effect size, and could even be in the wrong direction. And for a long time, people really didn't think seriously about these problems, which has led to a number of issues that we're now trying to address. And I think in general, it has led people to try to be more skeptical, right, about what is really the strength of the evidence that we're getting from a study or even from a field of studies. All right, any last questions? All right. So just a reminder, the TAs will be having their lab sections today. Please answer the poll in my email today as well if you can. And again, also feel free to contact me or the TAs at any time if you're having issues. For example, if you're having issues with accessing RStudio through your Wi-Fi, if you're falling behind on assignments, things like that, please let us know. We're here to help. All right. Have a great rest of the day, everybody.